There's a place in the universe where the laws of physics, as we know them, simply break. A place where gravity becomes so overwhelming that not even light can resist its pull. This is the event horizon, the point of no return for black holes. Cross this invisible boundary and there's no coming back. No signal, no cry for help, not even a whisper can escape. It's the universe's ultimate one-way door, and yet, despite its terrifying nature, the event horizon holds secrets that could reshape our understanding of reality itself. Think about that for a moment. We're talking about a region of space where time slows to a crawl, where matter is stretched and compressed into oblivion, and where the very fabric of spacetime is twisted beyond recognition. Black holes are cosmic enigmas, and their event horizons are the gatekeepers of these mysteries. What happens inside? Where does everything that falls in actually go? These questions have haunted scientists and stargazers alike for decades, and today we're diving deep into the science, the speculation, and the mind-bending truths about this invisible frontier. But here's the thing: black holes aren't just destructive monsters lurking in the void. They're also laboratories for some of the most extreme physics imaginable. From Hawking radiation to spacetime singularities, the event horizon is where the ordinary rules of the universe give way to something far stranger. And as our telescopes and simulations grow more advanced, we're getting closer than ever to unlocking these secrets. So if you've ever wondered what lies beyond the edge of a black hole, or how something so destructive could also be a key to understanding the cosmos, you're in the right place. Strap in, because we're about to journey to the very boundary of the unknown. To understand black holes, we have to start with the life and death of stars. Imagine a massive star, many times larger than our Sun, burning through its fuel over millions of years. When that fuel runs out, the star can no longer fight against its own gravity. In a final, cataclysmic moment, it collapses inward in a supernova explosion, an event so powerful it outshines entire galaxies for a brief instant. What remains after this violent death? If the core is dense enough, gravity crushes it down into an infinitely small point called a singularity, warping spacetime around it so severely that nothing, not even light, can escape its grasp. That's the birth of a black hole. The sheer power of a black hole's gravity is almost impossible to comprehend. It doesn't just pull, it distorts reality itself. Picture throwing a rock into a pond. The ripples spread outward, right? Now imagine if the pond's surface became so warped that the ripples couldn't escape. That's what happens near a black hole. Space and time are bent to their limits, creating a gravitational well with no bottom. And because light can't break free past the event horizon, black holes are effectively invisible, like cosmic ghosts. We can't see them directly, but we know they're there by the way they interact with everything around them. Stars orbiting empty space at mind-blowing speeds, gas swirling into nothingness, bursts of X-rays as matter is torn apart. These are the fingerprints black holes leave behind. Yet for something so destructive, black holes are strangely predictable. Their behavior follows the same laws of physics that govern the rest of the universe, just pushed to extremes. That's why scientists can study them, even from millions of light years away. By observing their effects on nearby stars or the radiation they emit, we've pieced together a surprisingly detailed picture of these invisible monsters. And with every discovery, we uncover more questions. What happens to matter inside a black hole? Does it vanish forever, or is there some way information escapes? These puzzles aren't just academic, they challenge our very understanding of reality. Gravity is the invisible architect of the cosmos, shaping everything from the orbits of planets to the fate of galaxies. But in the realm of black holes, gravity takes on a far more dramatic and mind-bending role. To grasp how this works, we have to go back to Einstein's revolutionary theory of general relativity. It tells us that gravity isn't just a force pulling objects together, it's the curvature of spacetime itself. Picture a stretched rubber sheet with a bowling ball placed in the center. The heavier the object, the deeper the dent it creates, pulling everything nearby toward it. Now imagine that bowling ball replaced by something unimaginably dense, like a black hole. The sheet doesn't just dip, it tears, creating a bottomless pit where the rules we know no longer apply. This extreme warping of spacetime around a black hole is why the event horizon exists in the first place. Once matter or light crosses that threshold, the slope becomes so steep that nothing can climb back out. Time itself behaves strangely here. To an outside observer, an object falling toward a black hole would appear to slow down, eventually freezing at the event horizon as if time had stopped. But from the perspective of the object falling in, time marches on normally right up until it's torn apart by tidal forces or crushed into the singularity. This bizarre disconnect between observers is one of relativity's most startling predictions, proving that time isn't just universal but elastic, stretching or compressing depending on gravity's grip. What makes black holes truly unique is how they push these effects to the absolute limit. Around a planet or a star, spacetime bends just enough to keep moons in orbit or sunlight streaming toward us. But near a black hole, the curvature becomes infinite. This is why physicists sometimes say black holes don't just bend spacetime, they puncture it. Matter gets stretched into spaghetti like strands in a process aptly named spaghettification, while the singularity at the core defies all known physics. Even Einstein himself struggled with the implications, initially doubting such objects could exist in reality. Yet decades of observations from the first detection of Cygnus X1 to the groundbreaking images of M87's shadow have confirmed they're not just theoretical nightmares but real cosmic phenomena. The deeper we probe, the more questions arise. For instance, if black holes warp spacetime so severely, could they create shortcuts through the universe like the wormholes of science fiction? Or do they hold clues to unifying gravity with quantum mechanics, bridging the gap between the very large and the unimaginably small? While we don't have all the answers yet, each discovery peels back another layer of the mystery. And that's the beauty of studying these gravitational monsters. They force us to rethink everything we thought we knew about the fabric of reality. So what exactly marks the edge of a black hole's darkness? The event horizon isn't a physical surface, it's a mathematical boundary, a point of no return where gravity's grip becomes irreversible. Imagine trying to swim upstream against a waterfall. At first, you might fight the current, but there's a moment when the water's pull becomes too strong, and no amount of effort can save you from being swept over the edge. The event horizon is like that tipping point, but instead of water, it's the fabric of spacetime itself dragging you inward. Here's the science behind it. Escape velocity, the speed needed to break free from an object's gravity, depends on how massive that object is and how close you are to it. For Earth, that speed is about 11 kilometers per second. But near a black hole, gravity intensifies so drastically that the required escape velocity eventually surpasses the speed of light, the universe's ultimate speed limit. And since nothing can travel faster than light, nothing, not even a beam of light fired outward at full power, can escape once it crosses that threshold. That's why the event horizon is often called a one-way membrane. Step across, and every possible path leads inward toward the singularity. But here's where it gets even stranger. The event horizon isn't just a static line in space, it's dynamic, shaped by the black hole's mass and spin. For a simple, non-rotating black hole, the event horizon forms a perfect sphere. But if the black hole spins, spacetime twists around it like a whirlpool, stretching the horizon into a bulging, asymmetrical shape. Matter and energy don't just fall straight in, they spiral violently like water circling a drain. And the faster the spin, the more distorted the event horizon becomes, creating regions where space itself is dragged along at nearly light speed. What does this mean for an object approaching the edge? From an outsider's perspective, time dilation effects become extreme. A clock falling toward the event horizon would appear to tick slower and slower, freezing completely at the boundary. Yet for the unlucky traveler, time feels normal right up until tidal forces stretch them apart atom by atom. This paradox hints at the bizarre interplay between gravity and time, one of Einstein's most profound revelations. The event horizon also holds clues to one of physics' biggest puzzles, the information paradox. According to quantum mechanics, information about particles can never be truly destroyed. But if matter vanishes past the event horizon, where does that information go? Some theories suggest it might be encoded on the horizon itself, like a cosmic hologram. Others propose it leaks back out as Hawking radiation, a faint glow of particles emitted by black holes over unimaginable timescales. These ideas aren't just speculative, they're reshaping our understanding of reality's deepest rules. So while the event horizon might seem like the end of the story, it's really just the beginning of a far stranger one. It's a laboratory for testing the limits of physics, a place where the familiar universe ends and the unknown begins. And as we peer closer through telescopes, equations, and simulations, we're not just studying black holes, we're decoding the universe's most dramatic secrets written in gravity's own hand. The closer you get to a black hole's event horizon, the stranger reality becomes. Gravitational time dilation, one of Einstein's most startling predictions, means time itself slows down near this invisible boundary. Picture two astronauts, one orbits at a safe distance while the other descends toward the black hole. From the orbiting astronaut's perspective, their companions' movements grow sluggish, like watching a video in slow motion. Their heartbeat, their speech, even the light reflecting off their suit, all of it stretches out, fading toward infinity as they approach the event horizon. But for the falling astronaut, time feels normal. Minutes pass as they always would, unaware that to the outside universe, their final moments are playing out over centuries. This isn't just theoretical. GPS satellites orbiting Earth have to account for tiny time dilation effects caused by our planet's gravity. A clock on Earth ticks slightly slower than one in space, a difference measurable in nanoseconds. But near a black hole, the effect escalates beyond imagination. At the event horizon, time dilation becomes infinite. From an outsider's viewpoint, nothing ever truly crosses. The falling astronaut appears frozen, a ghost haunting the edge forever. Yet inside, the plunge continues. This paradox reveals a core truth: time isn't universal. It bends, warps, and fractures under gravity's relentless pull. Light behaves just as strangely. As photons struggle against the black hole's gravity, they lose energy, stretching into longer, redder wavelengths, a phenomenon called gravitational redshift. Imagine shouting to a friend as you fall toward the event horizon. At first, they hear your voice normally, but as gravity's grip tightens, your words slow, deepening to a low rumble before fading into silence. Light follows the same path. What began as visible light shifts to infrared, then radio waves before vanishing entirely. The black hole doesn't just trap light, it rewrites its very signature, erasing it from the observable universe. Matter faces an even more violent fate: tidal forces. The difference in gravity's pull between your head and feet stretch and compress objects in a process called spaghettification. A star wandering too close isn't swallowed whole. Instead, it's shredded into a glowing stream of plasma, swirling into the abyss like water down a drain. These tidal forces are so extreme that molecular bonds snap like thread, reducing everything to its most basic particles long before reaching the singularity. Yet for all its destructive power, the event horizon isn't chaos. It follows precise mathematical rules, a frontier where general relativity and quantum mechanics collide. Quantum fluctuations near the horizon create particle-antiparticle pairs. Normally, they'd annihilate instantly, but if one particle falls in while the other escapes, the black hole appears to emit radiation, a glow predicted by Stephen Hawking. Over eons, this Hawking radiation causes black holes to evaporate, a slow leak of energy from the universe's darkest prisons. Here's the twist: Hawking radiation implies black holes aren't eternal. They have a temperature, a lifespan, and a fate. A stellar mass black hole might take longer than the current age of the universe to evaporate, but supermassive ones, their glow is so faint it's practically undetectable. Yet this microscopic process hints at a profound connection between gravity, quantum physics, and thermodynamics, a puzzle we're still unraveling. The event horizon isn't just a barrier. It's a cosmic classroom teaching us that space and time are fluid, that light can be rewritten, and that even the universe's most perfect traps might one day fade to nothing. Every photon stretched, every second bent, every particle split at the edge. These aren't just oddities. They're clues to a deeper reality written in the language of extreme gravity. The idea of black holes didn't spring up overnight. It's a story centuries in the making, woven through the minds of brilliant thinkers who dared to imagine the impossible. It begins in the late 1700s with a clergyman and scientist named John Michell. Picture this: a world where Newton's laws of gravity were still fresh revelations, and the concept of dark stars was pure speculation. Michell theorized that if a star were massive enough, its gravity might be so strong that light itself couldn't escape. He called these objects dark stars, and while his calculations were rough by today's standards, the seed of an extraordinary idea had been planted. For over a century, Michell's theory languished in obscurity until Einstein's general relativity rewrote our understanding of gravity in 1915. Suddenly, spacetime wasn't just a stage for the universe's events. It was a dynamic fabric that could bend, warp, and even tear. Just a year later, German physicist Karl Schwarzschild took Einstein's equations and applied them to an idealized scenario, a perfectly spherical, non-rotating mass. The result, a mathematical boundary where spacetime curvature became infinite, the first rigorous description of what we now call the event horizon. Tragically, Schwarzschild died shortly after this breakthrough, never knowing how pivotal his work would become. The mid-20th century transformed black holes from mathematical curiosities into serious astronomical possibilities. Physicists like Subrahmanyan Chandrasekhar wrestled with the fate of dying stars, calculating that beyond a certain mass, a collapsing star wouldn't settle as a dense remnant but keep crushing inward endlessly. J. Robert Oppenheimer, yes, the same man behind the atomic bomb, took this further, describing how a massive star's core could collapse past the point of no return. Yet many scientists, including Einstein himself, resisted the idea, convinced nature would find a way to prevent such absurdities. Everything changed in the 1960s and 70s. The term black hole was coined by physicist John Wheeler, capturing the public's imagination with its eerie simplicity. Meanwhile, discoveries like Cygnus X1, a mysterious X-ray source in our galaxy, provided the first indirect evidence of black holes. Astronomers realized these cosmic vacuum cleaners weren't just theoretical nightmares but real objects, lurking in the darkness and devouring anything that wandered too close. Telescopes grew sharper, and by the 21st century, we weren't just inferring black holes, we were seeing their shadows. The Event Horizon Telescope's landmark image of M87's supermassive black hole in 2019 was a triumph, revealing the glowing ring of light bent around the abyss. What's astonishing isn't just how far we've come, it's how each breakthrough was met with skepticism, then revolution. From Michell's ink and paper musings to gravitational wave detectors picking up black hole collisions, the journey has been anything but linear. And with every answer, new questions emerge. How do supermassive black holes form so early in the universe's history? What happens to the information they swallow? These aren't just puzzles for astrophysicists, they're clues to the fundamental nature of reality itself. The history of black holes is a testament to human curiosity, a reminder that sometimes the universe's strangest truths start as whispers in the dark. Einstein saw black holes as terrifying endpoints, cosmic one-way streets where matter and energy vanished forever. His equations predicted the event horizon, but he struggled with the idea that nature would permit such infinite, destructive collapse. After all, if nothing could escape, where did all that information go? It was a paradox that haunted him, clashing with his belief in a universe governed by elegant, unbreakable laws. To Einstein, the event horizon was a mathematical boundary where physics, as we understood it, simply gave up. Then came Stephen Hawking, who turned this notion on its head. In the 1970s, he proposed something radical: black holes aren't completely black. At the quantum level, just outside the event horizon, pairs of virtual particles flicker in and out of existence. Normally, they annihilate each other instantly, but Hawking realized that if one particle fell into the black hole while its partner escaped, the escaping particles would carry away energy, slowly bleeding the black hole dry. This Hawking radiation meant black holes had a temperature, a lifespan, and could eventually evaporate. It was a revelation that shook physics to its core. Suddenly, the event horizon wasn't just a grim endpoint. It was a dynamic surface buzzing with quantum activity. Hawking's theory introduced a bizarre contradiction. If black holes evaporate, what happens to all the information they swallowed? Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it permanently. This became the infamous information paradox, sparking debates that still rage today. Einstein might have recoiled at the idea, seeing it as a violation of determinism, the idea that the past perfectly predicts the future. Yet Hawking's work opened doors to even stranger possibilities. If black holes emit radiation, do they also preserve information in some scrambled form? Could the event horizon act like a hologram, encoding data about everything that fell in? These questions forced physicists to bridge the gap between general relativity and quantum mechanics, two pillars of modern science that refuse to play nicely together. Einstein's gravity described the large-scale warping of spacetime, while quantum mechanics ruled the subatomic world. Hawking radiation was one of the first clues that these realms might not be separate at all. The contrast between these two giants couldn't be starker. Einstein's black holes were silent, eternal tombs. Hawking's were leaky, decaying objects with a hidden connection to the quantum world. One saw the event horizon as a fatal boundary, the other saw it as a bubbling quantum firewall. And while Einstein might have doubted black holes even existed, Hawking's theories helped convince the world they were not just real, but far weirder than anyone imagined. Today, this debate is far from settled. Some physicists argue Hawking radiation resolves the information paradox, while others propose even wilder ideas, like black holes birthing new universes or containing hidden portals to other dimensions. What's clear is that the event horizon remains one of science's greatest battlegrounds, where the legacies of Einstein and Hawking continue to collide. Their disagreements weren't just academic, they were a roadmap to deeper truths, pushing us to question whether the universe plays by rules we've yet to fully grasp. Spaghettification might sound like a silly word, but it describes one of the most violent and bizarre phenomena in the universe. Picture an astronaut drifting too close to a black hole's event horizon. At first, nothing seems unusual until the difference in gravity's pull between their head and feet becomes extreme. Their body begins to stretch, limbs elongating like taffy, while their sides compress inward. Within moments, they're transformed into a thin, noodle-like strand of atoms, a human spaghetti filament spiraling into the abyss. It's a fate as dramatic as it is inevitable near these cosmic monsters. The science behind this process is rooted in tidal forces, the same phenomenon that causes Earth's ocean tides. The Moon's gravity pulls more strongly on the side of Earth facing it, stretching the planet slightly and creating bulges in our oceans. But near a black hole, these forces aren't gentle nudges, they're catastrophic. A stellar mass black hole might exert tidal forces billions of times stronger than anything in our solar system. The difference in gravity between your head and feet would be so immense that your body wouldn't just feel stretched, it would be ripped apart at the molecular level before you even crossed the event horizon. What's fascinating is how this plays out for different-sized black holes. Counterintuitively, smaller black holes are far deadlier. A black hole with the mass of our Sun would shred you thousands of miles away from its event horizon. But a supermassive black hole, like the one at the center of our galaxy, has a more gradual gravity gradient. You could theoretically cross its event horizon intact at least briefly before tidal forces inevitably tore you apart deeper inside. It's a grim irony. The most massive black holes might offer a few extra moments of survival, but the end result is always the same. This violent stretching isn't limited to unlucky astronauts. Stars that wander too close suffer the same fate in events called tidal disruption flares. Gas and plasma are pulled into swirling arcs, heating to millions of degrees and glowing brightly before vanishing past the event horizon. Telescopes have captured these cosmic meals in action, flares of X-rays and ultraviolet light marking the last screams of matter being consumed. The real mind-bender is what happens next. Those stretched-out atoms don't just vanish, they accelerate to near light speeds, colliding with other particles in a frenzy of energy. Friction heats the plasma to incredible temperatures, creating an accretion disk that can outshine entire galaxies. It's a brutal recycling program where stardust becomes fuel for the universe's most efficient engines. Spaghettification isn't just a gruesome cosmic spectacle. It's a stark reminder of how black holes warp reality itself, turning the familiar into the alien. Matter isn't just crushed, it's rewritten, stretched across space-time in ways that defy imagination. And as we study these extreme transformations, we're not just learning about destruction. We're uncovering the universe's most fundamental rules written in the unraveling of atoms at the edge of oblivion. Black holes might seem like the ultimate cosmic prisons, but nature has a few tricks up its sleeve, ways for particles to slip through the cracks of even the most unforgiving event horizons. Take Hawking radiation, for example. It's not some fiery jet or explosive burst. Instead, it's a ghostly whisper of energy born from the bizarre interplay of quantum physics and gravity. Here's how it works. Just outside the event horizon, pairs of virtual particles constantly flicker in and out of existence. Normally, they annihilate each other instantly. But if one particle falls into the black hole while its partner escapes, the black hole loses a tiny bit of mass. Over billions of years, this slow leak could cause the black hole to evaporate entirely, a revelation that flipped our understanding of these cosmic monsters on its head. Then there's quantum tunneling, a phenomenon so strange it feels like cheating nature's rules. Imagine a ball rolling up a hill. Classically, it needs enough energy to reach the top. But in the quantum world, there's a small chance the ball could simply tunnel through the hill without ever going over it. Near a black hole, particles can theoretically pull off the same stunt, bypassing the event horizon's grip entirely. The odds are astronomically low, but given enough time and enough particles, tunneling suggests that even black holes aren't perfect traps. These exceptions aren't just curiosities, they're clues to something deeper. If particles can escape, what happens to the information they carried in? Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it. This paradox has led to wild theories, like the idea that escaping particles carry scrambled fragments of that information, or that it's preserved on the event horizon itself like a cosmic hard drive. Some physicists even suggest black holes might be gateways, not in points their interiors warping into entirely new universes where the rules are rewritten. Of course, none of this means black holes are harmless. For anything larger than a subatomic particle, the event horizon remains a one-way trip. But these tiny loopholes remind us that the universe rarely deals in absolutes. Even in the darkest corners of space, physics finds a way to surprise us, turning what we thought were dead ends into doorways for discovery. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, an invisible titan millions or even billions of times heavier than our Sun. These cosmic behemoths don't just sit quietly in the dark. Their event horizons act like gravitational anchors, shaping the destiny of stars, gas, and entire star systems around them. Take Sagittarius, a star, the supermassive black hole at our galaxy's core. Though its event horizon spans just 20 million kilometers, a speck compared to the Milky Way's vastness, its influence stretches across light years, orchestrating the chaotic dance of matter spiraling toward oblivion. The sheer scale of these giants defies intuition. Unlike stellar black holes formed from collapsing stars, supermassive black holes grow over billions of years, gorging on gas, dust, and even other black holes. Their event horizons become gravitational engines, converting stolen matter into blinding energy. When gas clouds or stars venture too close, tidal forces rip them apart, feeding the black hole's accretion disk, a swirling inferno of plasma hotter than a million suns. The energy released can outshine every star in the galaxy combined, creating phenomena like quasars, nature's most powerful lighthouses. These outbursts don't just vanish into the void. They sculpt galaxies, heating surrounding gas so intensely that star formation shuts down across entire regions. Yet for all their destructive power, supermassive black holes might also be galactic guardians. Observations reveal a curious link between a galaxy's size and the mass of its central black hole, as if the two grew in lockstep. One theory suggests that jets of particles screaming away from the event horizon act like cosmic regulators, pumping energy back into the galaxy. By preventing runaway star formation, these jets might maintain equilibrium, ensuring galaxies don't burn out too quickly. It's a delicate balance, too active, and the black hole sterilizes its surroundings, too quiet, and stars form unchecked, exhausting the galaxy's fuel. The event horizons of these giants also serve as cosmic time capsules. As matter falls in, it carries traces of the galaxy's history, chemical fingerprints of ancient stars, echoes of long-dead quasars. Even light orbiting just outside the horizon, like photons trapped in a gravitational ballet, can reveal secrets about the black hole's spin and mass. Scientists are already using this data to map spacetime's warping with unprecedented precision, turning these dark hearts into laboratories for testing relativity itself. Perhaps most astonishing is how supermassive black holes shape galactic architecture. Stars near Sagittarius, a star whip around at thousands of kilometers per second, their orbits betraying the black hole's presence like moths circling a flame. Over eons, these gravitational interactions can fling stars out of the galaxy entirely or herd them into dense clusters. Some theories even suggest that collisions between galaxies and their central black holes might trigger new epochs of cosmic evolution, seeding the universe with fresh structures. The event horizon isn't just a boundary, it's a fulcrum leveraging gravity's might to mold galaxies from the inside out. Whether as destroyers, regulators, or architects, supermassive black holes prove that darkness isn't empty. It's alive with forces that build and obliterate in equal measure, writing the story of the cosmos one fallen star at a time. Time doesn't just slow down near a black hole's event horizon, it fractures into something unrecognizable. Picture a clock falling toward that invisible boundary. From the perspective of someone watching from a safe distance, the clock's ticking would stretch out longer and longer, like a record player gradually winding down. The seconds between each tick grow wider, the hands moving slower until finally, at the very edge of the horizon, time appears to freeze completely. to an outside observer, nothing ever truly crosses. The clock hangs there, suspended, as if the universe itself has pressed pause. But here's the twist: for the clock itself, time marches on normally. If you were riding along with it, your wristwatch would keep perfect time, ticking away without hesitation. You wouldn't feel any slowdown, any cosmic hesitation, just the relentless pull of gravity carrying you forward. This bizarre disconnect isn't just a quirk of black holes. It's a fundamental feature of Einstein's general relativity. Gravity doesn't just bend space, it warps time, stretching and compressing it like taffy. Near the event horizon, the warping becomes so extreme that time splits into two realities, one for the falling object, one for the distant observer. Let's put this into perspective. Imagine an astronaut foolish enough to dive toward a black hole while their partner waits in orbit. For the orbiting astronaut, watching their friend descend would be like witnessing a slow-motion nightmare. The falling astronaut's movements would crawl, their speech dragging into a deep, distorted groan as light struggles to escape the black hole's gravity. After just a few minutes of this agonizing display, the orbiting astronaut might check their own watch only to realize years, even centuries, have passed back on Earth. Entire civilizations could rise and fall in the time it takes their companion to vanish from view. This effect isn't science fiction. We see milder versions of it every day. The GPS satellites guiding your phone's navigation have to account for time dilation caused by Earth's gravity. A clock on Earth ticks ever so slightly slower than one in orbit, a difference of microseconds, but enough to throw off navigation by miles if uncorrected. Black holes crank this effect to unimaginable extremes. Near a stellar mass black hole, aging just 1 hour could mean returning to a galaxy where everyone you knew has been dead for millennia. What's truly mind-bending is how this ties into the black hole's insatiable hunger. As matter approaches the event horizon, the light it emits gets stretched to longer, redder wavelengths, a phenomenon called gravitational redshift. Colors shift from blue to red to infrared, fading into invisibility as the photons lose energy fighting gravity's pull. The same happens to time. Events near the horizon unfold so slowly from an outsider's view that the black hole's entire lifetime, trillions of years of Hawking radiation decay, could pass before the falling object even seems to reach the edge. In a sense, the universe outside fast-forwards, leaving the doomed traveler forever stuck in the dying embers of a single, stretched-out moment. Yet this isn't just a cosmic horror story. Time dilation at the event horizon offers physicists a unique laboratory. By studying how light and matter behave under such extreme conditions, we're testing the limits of relativity itself. Could time really stretch infinitely at the horizon, or does quantum mechanics step in to prevent it? Does information get smeared across the boundary, or is it locked away forever? These questions aren't abstract, they push us toward a deeper theory of gravity, one that might finally bridge the gap between the cosmic and the quantum. The event horizon doesn't just warp time, it bends our understanding of reality. Studying black holes directly is impossible. They're invisible, distant, and utterly hostile to anything that gets too close. So how do scientists unravel the mysteries of event horizons without taking a suicidal plunge? The answer lies in simulation, where cutting-edge technology lets us recreate these cosmic monsters in the safety of labs and supercomputers. One of the most powerful tools in this virtual arsenal is numerical relativity, a field that uses mind-bending mathematics to model spacetime's behavior around black holes. Picture a supercomputer crunching Einstein's equations at scales so precise they can simulate the warping of spacetime itself, frame by frame. These simulations don't just produce static images, they generate dynamic, evolving landscapes where black holes spin, collide, and devour matter in hyper-detailed virtual scenarios. But math alone isn't enough. To test these models, we need real-world data, and that's where gravitational wave observatories like LIGO come in. When two black holes spiral toward each other, their immense gravity ripples spacetime like a boat's wake, sending out waves that travel across the universe. LIGO ultra-sensitive lasers detect these faint tremors, allowing scientists to compare their simulations with actual cosmic events. The first detection in 2015 was a revelation. The chirp of two black holes merging matched simulations almost perfectly, proving that Einstein's century-old equations could predict the unseeable. Since then, dozens of collisions have been recorded, each one refining our understanding of how event horizons behave under extreme conditions. Yet some questions demand even wilder experiments. Take fluid dynamics laboratories, where scientists create analog black holes using water vortices or supercooled quantum fluids. In these setups, swirling drains or pulses of light mimic an event horizon's gravity, trapping sound waves or photons just like a real black hole traps light. It's a clever workaround using water or light to simulate spacetime's curvature, and it's helped researchers explore phenomena like Hawking radiation in controlled settings. These analog systems can't replicate a black hole's full horror, but they offer tantalizing glimpses into how particles might behave at the edge. Then there's the Event Horizon Telescope, a global network of observatories that essentially turns Earth into a planet-sized radio dish. In 2019, it captured the first ever image of a black hole's shadow, the dark silhouette of M87's event horizon, ringed by glowing gas. That image wasn't just a pretty picture, it was a direct test of general relativity. The size and shape of the shadow matched predictions down to the pixel, giving us visual proof that Einstein's theory holds even in gravity's most extreme arena. What's striking about these methods is how they complement each other. Supercomputers simulate the math, gravitational waves provide the soundtrack, analog models tease out quantum effects, and telescopes deliver the visuals. Together, they're piecing together a portrait of the invisible, a map of the universe's most forbidden frontier. And with each breakthrough, we're not just learning about black holes. We're stress-testing the very laws of physics, probing the limits of human knowledge from the safety of our own cosmic backyard. On April 10, 2019, humanity saw the impossible, a shadow against the glow of space, a silhouette so dark it defied physics. The Event Horizon Telescope collaboration unveiled the first ever image of a black hole's event horizon, capturing the supermassive beast at the heart of galaxy M87. This wasn't just a photograph, it was a cosmic fingerprint confirming a century of theory while revealing details no equation could predict. The now iconic image showed a bright ring of orange-yellow light superheated gas swirling at nearly the speed of light, wrapped around a perfect circle of darkness. That central void was the black hole's shadow, a region roughly 2.5 times larger than the actual event horizon where light bends so severely it can't reach us. What made this image revolutionary wasn't just its existence. The shape and size of that glowing ring matched Einstein's predictions with astonishing precision. General relativity had passed its most extreme test yet, proving spacetime warps exactly as calculated, even when gravity is strong enough to swallow stars whole. But there were surprises too. The ring wasn't uniform. One side blazed brighter than the other, a phenomenon called Doppler beaming caused by gas hurtling toward us on one side of the disk while receding on the other. This asymmetry revealed the black hole's spin, showing how it drags spacetime around it like a whirlpool. The sheer scale of the effort behind this image is staggering. The Event Horizon Telescope wasn't a single observatory but a network of 8 radio telescopes spanning from Hawaii to the South Pole, synchronized to function as a virtual dish the size of Earth itself. Each telescope collected petabytes of data, so much that physical hard drives had to be flown to central processing facilities, as transferring files digitally would have taken years. Astronomers then spent months painstakingly stitching together the fragments, like assembling a jigsaw puzzle with pieces scattered across the globe. But beyond the technical triumph, this image shifted how we perceive black holes. No longer were they just mathematical abstractions or artists' renditions. That eerie orange ring made them tangible, proving Einstein right while leaving new questions in its wake. Why, for instance, was the ring brighter than models predicted? Could there be unexpected physics at play near the event horizon, or was it simply a matter of how the accreting gas behaved? The image also hinted at magnetic fields threading through the chaos, invisible lines of force shaping the plasma's flow in ways we're only beginning to understand. Perhaps most remarkably, this single snapshot opened a new era of black hole astronomy. Since 2019, the Event Horizon Telescope has turned its gaze toward other targets, including Sagittarius, a star, the supermassive black hole at our galaxy's heart. Each observation peels back another layer, transforming event horizons from theoretical boundaries into dynamic laboratories where gravity, plasma physics, and quantum mechanics collide. That first image wasn't an endpoint, it was a doorway, proving that even the universe's darkest secrets can't hide forever when human ingenuity shines a light. If black holes are cosmic vacuum cleaners, relentlessly sucking everything in, then white holes are their theoretical opposites, cosmic fire hoses spraying matter and energy outward with unstoppable force. These hypothetical objects are born from the same equations that predict black holes, but with time playing in reverse. Where an event horizon traps everything inside a black hole, a white hole's horizon would repel everything, refusing entry to anything trying to cross from the outside. Not even light could penetrate. The idea emerges from a daring thought experiment. What if you could rewind a black hole's life like a film in reverse? Instead of matter collapsing inward, it would erupt outward, blasting energy and particles into space in a violent cascade. Mathematically, this flip is perfectly valid within Einstein's general relativity. Some theories even suggest that a black hole's singularity might connect to a white hole through a spacetime tunnel, creating a bridge between 2 points in the universe or even between separate universes entirely. But here's the catch. While black holes are inevitable endpoints for massive stars, white holes face a glaring problem with thermodynamics. Nature tends toward entropy, the gradual spreading out of energy, yet white holes would concentrate energy in explosive outbursts, defying the universe's preference for disorder. There's also no known process that could create one. Black holes form from collapsing stars, but white holes would need some mechanism to uncollapse, reversing gravity's pull in a way that seems impossible based on everything we've observed. That hasn't stopped physicists from exploring the idea. Some speculate that white holes could explain mysterious cosmic explosions, like fast radio bursts or gamma-ray bursts, whose origins remain partly unexplained. Others suggest that if black holes eventually evaporate via Hawking radiation, their final moments might resemble a white hole's explosive end, a last gasp of energy before fading to nothing. Perhaps the most tantalizing version of the white hole hypothesis ties into quantum gravity. If black holes don't destroy information but somehow preserve it, a white hole could be the mechanism that releases it back into the universe, like a cosmic recycling plant turning destruction into rebirth. It's a poetic idea, though still far from confirmed. For now, white holes remain a fascinating what-if of theoretical physics, a reminder that the universe's strangeness might still outpace our boldest imaginations. They push us to question whether every endpoint must be final, or if somewhere beyond the event horizon, physics has a trick up its sleeve we've yet to uncover. The notion of slipping across the universe through a cosmic shortcut sounds like pure science fiction until you dig into the math. Wormholes, those hypothetical tunnels through spacetime, emerge from the same equations that describe black holes and their event horizons. Picture space as a vast sheet of paper with 2 distant points folded together. A wormhole would be like poking a pencil through that fold, creating a bridge that bypasses the normal rules of distance. And here's where things get wild. Some theories suggest these shortcuts might naturally link to black holes, turning their event horizons from dead ends into gateways. But don't pack your interstellar suitcase just yet. For a wormhole to be traversable, it would need to stay open long enough, and that requires something exotic. Negative energy or matter with repulsive gravity could theoretically prop the tunnel open against collapse. The problem, no one's ever found proof such materials exist. Even if they did, the forces near a black hole's event horizon would likely shred anything attempting the journey. The tidal forces that spaghettify stars wouldn't politely pause for travelers. And then there's the small matter of causality. If you could dart through a wormhole and emerge before you left, you'd violate the universe's strict no-time travel policy, creating paradoxes that make physicists shudder. Yet the idea isn't entirely far-fetched. Take the Einstein-Rosen bridge, a theoretical link between black holes proposed in 1935. It suggested that the singularity inside a black hole might connect to a white hole's explosion elsewhere, or even in another universe. Modern refinements like traversable wormholes stabilized by quantum fields keep the dream alive. Some researchers even speculate that advanced civilizations could engineer stable wormholes using technologies far beyond our grasp to neutralize the deadly physics. The real kicker, wormholes might already be hiding in plain sight. Some models suggest microscopic versions could flicker in and out of existence at the quantum level, woven into the fabric of spacetime itself. If we could somehow harness these fleeting tunnels, stretching them, reinforcing them, they'd revolutionize exploration. Imagine stepping through a portal near Earth and emerging near Proxima Centauri, bypassing light years in an instant. It's the ultimate cheat code for the cosmos. Of course, the hurdles are astronomical, but that's the beauty of theoretical physics. It doesn't just describe the universe we know. It dares to imagine the one we don't. Whether wormholes remain mathematical curiosities or future highways among the stars, they remind us that the universe's rulebook might still have chapters we haven't read. And if there's one place to look for those answers, it's at the edge of an event horizon where the known and the unknown collide. Einstein's general relativity paints the event horizon as a smooth, uneventful boundary, a mathematical line where gravity's grip becomes absolute. But quantum mechanics tells a radically different story. At the tiniest scales, the vacuum of space isn't empty at all. It's a seething foam of virtual particles popping in and out of existence, a quantum frenzy that should make the event horizon anything but serene. This clash isn't just academic, it's a battle for the soul of physics, forcing us to ask, what really happens at the edge of a black hole? Take Hawking radiation, the quantum glitch that first exposed this rift. According to quantum theory, particle-antiparticle pairs constantly flicker near the horizon. If one falls in while the other escapes, the black hole loses energy, slowly evaporating over eons. But here's the paradox. General relativity insists the horizon has no special features, no fireworks, no particle pairs, just the quiet inevitability of spacetime's curvature. So which is it, a placid slope into darkness or a crackling quantum storm? The equations can't agree and the stakes couldn't be higher. If both theories are correct in their domains, why do they break down precisely where they should meet? The heart of the conflict lies in information. Quantum mechanics treats information as sacred. It can never be destroyed, only scrambled, but black holes seem to erase it blatantly. Toss a book into one, and according to relativity, its words are crushed into the singularity, lost forever. Hawking initially thought radiation carried no trace of that information either, implying it vanished from the universe, a heresy to quantum physicists. This information paradox sparked decades of debate, with luminaries like Leonard Susskind arguing the data must be encoded on the horizon itself, etched into its surface like a hologram. Others, like Roger Penrose, propose wilder solutions like quantum hair, subtle distortions in spacetime that preserve data in ways we can't yet detect. Then there's the firewall hypothesis, perhaps the most startling twist in the saga. In 2012, physicists Ahmed Olmary, Donald Marolf, and others suggested the event horizon might be a lethal wall of high-energy particles, a literal ring of fire incinerating anything that crosses. The reasoning: to reconcile quantum entanglement's rules with relativity's smooth horizon, something drastic had to give. The idea horrified many, including Hawking, who quipped, "There are no firewalls, just poor calculations." Yet it underscored the desperation in the field. When two bedrock theories collide, even the unthinkable becomes plausible. Could string theory or loop quantum gravity resolve this mess? String theory posits that particles aren't dots but vibrating strings, potentially smoothing over the contradictions. Some models suggest black holes are tangled knots of these strings, with horizons that blur into fuzzy quantum surfaces. Loop quantum gravity, meanwhile, imagines spacetime as a network of woven threads, a fabric that might fray or stretch at the horizon, allowing information to leak through. Both remain unproven, but they share a tantalizing promise, a framework where gravity and quantum weirdness finally shake hands. What makes this conflict so thrilling is its sheer audacity. We're not arguing over minor gaps in data, but foundational truths about reality. Is spacetime continuous or granular? Is information indestructible, or can black holes erase it? The event horizon isn't just a physical boundary, it's a philosophical frontier, forcing us to confront how little we truly grasp. And until we crack this puzzle, black holes will remain more than cosmic oddities. They're the ultimate test of whether our laws of physics are threads of a deeper tapestry or fragments of a picture we've yet to see whole. Physics thrives on one unshakable rule: information can never be destroyed, only transformed. Toss a book into a fire, and while the pages may burn, the information, the words, the meaning isn't truly gone. It's scattered into the smoke and ash, theoretically recoverable if you could track every particle. But black holes throw this principle into chaos. When matter crosses an event horizon, it's crushed into a singularity, leaving no trace of its original form. According to general relativity, that information vanishes forever, erased from the universe as if it never existed. This clash between quantum mechanics and gravity is the black hole information paradox, and it's one of the most heated debates in modern physics. The roots of the problem trace back to Stephen Hawking's groundbreaking work in the 1970s. His calculations suggested that black holes emit radiation and eventually evaporate, leaving nothing behind, no remnants, no hidden data. If true, this meant the universe had a cosmic delete button, violating quantum mechanics' core tenet that information must be preserved. The implications were staggering. If black holes could erase information, the entire framework of quantum theory, the foundation of everything from chemistry to computing, would need rewriting. Physicists split into camps. Some, like Hawking, initially believed information was truly lost. Others, like Leonard Susskind, argued fiercely that the universe couldn't possibly work that way. Enter the holographic principle, a radical idea born from string theory. It proposes that all the information swallowed by a black hole isn't lost but encoded on its event horizon like a cosmic DVD. Just as a hologram stores a three-dimensional image on a two-dimensional surface, the horizon might hold a map of everything that fell in. In this view, the black hole's surface buzzes with quantum bits, each storing tiny fragments of data. As Hawking radiation escapes, it carries this information away, scrambled but intact. The paradox isn't resolved by changing gravity or quantum mechanics, but by reimagining spacetime itself as a projection of deeper, lower-dimensional reality. But not everyone's convinced. Critics point out that if information escapes via Hawking radiation, it's so thoroughly scrambled that reconstructing it would require near-infinite time and precision. Others propose wilder solutions, like black holes birthing baby universes, where the information isn't lost but whisked away to another cosmic domain. Then there's the firewall hypothesis, suggesting the event horizon isn't smooth but a searing wall of energy that vaporizes in falling matter, preserving information at the cost of relativity's elegance. This isn't just academic squabbling. The paradox forces us to confront whether spacetime is continuous or pixelated, whether black holes are ultimate prisons or cosmic translators. Every proposed solution, holography, firewalls, wormholes, pushes the boundaries of known physics, revealing how much we still don't understand. And until we crack it, black holes remain more than cosmic oddities. They're the universe's most provocative riddles, challenging us to rewrite the rules of reality itself. Black holes and their event horizons have long captivated storytellers, transforming from obscure mathematical curiosities into cinematic spectacles that shape how we imagine the cosmos. Take Christopher Nolan's Interstellar, a film that didn't just feature a black hole but made its event horizon a central character. Gargantua, the movie's supermassive black hole, was rendered with painstaking accuracy by physicist Kip Thorne's equations, its swirling accretion disk and gravitational lensing effects mirroring real astrophysics. Yet the film also took creative liberties, like portraying the interior of the event horizon as a tessellated, time-bending library, a poetic but scientifically speculative twist. This blend of fact and fiction reflects a deeper tension. How do you dramatize the unknowable without betraying its mystery? Hollywood's love affair with black holes often leans into their apocalyptic potential. In The Black Hole, 1979, the Event Horizon became a gateway to a hellish realm, while Event Horizon 1997 reimagined it as a literal door to chaos, blending science fiction with horror. These portrayals tap into a primal fear, the idea of being trapped, erased, or consumed by forces beyond comprehension. Yet they also simplify. Real event horizons don't glow like fiery maelstroms or crackle with lightning. They're invisible, defined by absence rather than spectacle. The discrepancy matters because it shapes public expectations, leading some to wonder why actual telescope images, like the EHT's snapshot of M87, lack Hollywood's pyrotechnics. But pop culture isn't just about distortion, it's a gateway to curiosity. Interstellar's black hole ignited public interest in relativity, sending viewers down rabbit holes of research about time dilation and spacetime warps. Even Doctor Who's whimsical takes, like treating black holes as prisons for cosmic entities, spark questions about what might really lurk beyond the horizon. These stories serve as metaphors too. The event horizon's irreversibility mirrors life's pivotal moments, decisions that can't be undone, points of no return in relationships or history. The challenge lies in balancing awe with accuracy. When films like Ad Astra show astronauts skirting a black hole's edge, they trade realism for tension, amplifying the danger of tidal forces. Yet documentaries like Black Hole Apocalypse (PBS) counter this by grounding audiences in actual science, using simulations to show how a black hole's gravity would really stretch a starship. Both approaches have value. One fuels imagination, the other nurtures understanding. Perhaps the most enduring legacy of these portrayals is how they redefine our relationship with cosmic terror. A black hole's event horizon isn't just a death trap. In stories, it's a crucible for transformation. Whether it's Matthew McConaughey's Cooper transmitting quantum data from beyond the veil or Contact's wormhole journey, these narratives suggest that beyond the horizon lies not oblivion but revelation. Science hasn't proven that, of course, but in the space between equations and celluloid, wonder thrives. And sometimes that's enough to pull us closer to the real mysteries waiting at the edge of the unknown. The next decade promises to revolutionize our understanding of black holes and their enigmatic event horizons, thanks to a new generation of telescopes and missions pushing the boundaries of observation. Leading the charge is the James Webb Space Telescope, whose infrared eyes peer through cosmic dust to study the violent dances of matter around supermassive black holes with unprecedented clarity. Unlike Hubble's visible light focus, Webb detects the heat signatures of gas swirling at relativistic speeds just outside event horizons, revealing details about their feeding habits, spin rates, and how they warp spacetime in their vicinity. Already, it's captured stunning data on galaxies like Messier 74, where black hole outflows sculpt star-forming regions like cosmic fingerprints. But Webb isn't working alone. The upcoming European Space Agency's Athena X-ray Observatory, launching in the 2030s, will map the million-degree temperatures of accretion disks with spectral precision, tracing elements like iron as they spiral toward oblivion. Meanwhile, NASA's next-generation X-ray mission, LINX, aims to study the faintest echoes of black hole mergers, ripples in spacetime that could reveal how event horizons deform during collisions. These missions complement gravitational wave detectors like LISA, a space-based observatory set to launch in the 2030s that will listen for the low-frequency hum of merging supermassive black holes, events too colossal for Earth-bound instruments to detect. Together, they form an interstellar symphony of sensors, each instrument revealing a different movement in black holes' chaotic ballet. On the ground, the extremely large telescope, ELT, now under construction in Chile, will use its 39-meter mirror, nearly 4 times wider than today's largest telescopes, to track stars whipping around Sagittarius, a star at 30% the speed of light. By plotting these frenzied orbits year after year, astronomers hope to detect subtle deviations that might hint at unseen physics near the event horizon, like quantum fluctuations or hidden dimensions. Even radio astronomy is leaping forward. The next phase of the Event Horizon Telescope project aims to add space-based antennas, creating a virtual dish larger than Earth itself to capture razor-sharp videos of black holes in action, not just snapshots. Perhaps the most radical frontier lies in quantum gravity experiments. Labs like Fermilab are using superconducting sensors to hunt for minuscule spacetime, foam at the Planck scale, a grainy texture that might manifest near event horizons. Others are simulating black hole conditions using Bose-Einstein condensates or graphene sheets, where electrons mimic the behavior of particles near horizons. These tabletop experiments won't recreate a black hole's crushing gravity, but they could reveal how quantum mechanics twists spacetime at its most extreme. The ultimate goal, to witness a black hole's birth or death in real time. While stellar mass black holes form in seconds during supernova, their supermassive counterparts grow over billions of years, a timescale hopelessly slow for human observation. But with enough data, we might catch a middleweight black hole in the act of formation, or detect the final pops of evaporating primordial black holes via their Hawking radiation. Every new tool brings us closer to answering the existential questions. What lies beyond the event horizon's veil? Does spacetime fracture there, or does it bend into something stranger? The answers won't just satisfy curiosity, they'll rewrite textbooks, proving once again that the universe's darkest corners shine brightest with discovery. The idea of sending humans anywhere near a black hole sounds like science fiction, and for now it is, but let's indulge the fantasy for a moment. What would it actually take to approach an event horizon, and what would we face if we tried? The short answer, a nightmare of physics and engineering hurdles, each more daunting than the last. First, there's distance. Even the closest known black hole, Gaia BH1, lurks about 1,500 light-years away. With today's propulsion technology, a one-way trip would take tens of thousands of years. Even theoretical concepts like nuclear pulse propulsion or antimatter engines might only get us to a fraction of light speed, turning the journey into a multi-generational odyssey. Then there's the black hole itself. Picture a spacecraft creeping toward the event horizon of a stellar mass black hole. Long before crossing the boundary, tidal forces would wrench the ship apart, stretching it like taffy while compressing it sideways, a process as violent as it is inevitable. The gravitational gradient near smaller black holes is so extreme that the difference in pull between your head and feet would measure in the thousands of Earth gravities. No known material could withstand that strain. Even if we aimed for a supermassive black hole like Sagittarius, a star where tides are gentler near the horizon, survival would hinge on another grim reality: time dilation. To observers back on Earth, your approach would slow to a crawl. Hours for you could mean decades or centuries passing at home. By the time you neared the horizon, everyone you'd ever known would be dust. Meanwhile, the black hole's gravity would distort light into bizarre patterns. The universe behind you would appear to shrink and blue shift into a bright dot overhead, while the abyss below would yawn wider, swallowing your view. Communication would be impossible. Any signal you sent would redshift into oblivion, fading to undetectable wavelengths before reaching the outside world. But suppose we overcome all this. Suppose some future civilization builds a ship that can endure the tides, the radiation, the isolation. What then? Crossing the event horizon would be less like stepping through a gate and more like drifting past an invisible threshold where all possible paths lead inward. You wouldn't feel anything special at the moment of crossing, no jolt, no flash, but there'd be no turning back. Any attempt to fire your engines would only hasten your doom, as spacetime itself flows toward the singularity faster than light can escape. The real tragedy: you'd never even see the singularity coming. In the black hole's warped spacetime, the future isn't ahead of you. It's literally below you, an inevitable point in space you'd fall toward like a marble rolling into a pit. The laws of physics as we know them break down there, leaving us with no way to predict what happens next, crushed into infinite density, spaghettified into a stream of particles. Maybe something stranger. The irony is thick. The only way to learn the truth would be to take a leap no one could ever report back from. So while Hollywood loves the drama of black hole plunges, reality paints a bleaker picture. For now, and likely centuries to come, these cosmic monsters will remain places we study from afar, through telescopes, simulations, and the faint whispers of gravitational waves. And perhaps that's for the best. Some frontiers aren't meant to be crossed. Some mysteries are better left to the universe. Dark matter, the invisible glue holding galaxies together, has teased astronomers for decades. It doesn't emit, absorb, or reflect light, revealing itself only through gravitational tugs on stars and gas. But what if black holes, those gravitational monsters lurking in cosmic shadows, hold clues to this enigma? Some theories suggest event horizons might not just trap matter, they could also interact with dark matter in ways we're only beginning to unravel. Imagine dark matter as a ghostly ocean, its particles drifting through space without a whisper. Unlike normal matter, these particles rarely collide with each other or anything else, hence their invisibility. But near an event horizon, gravity's pull is so intense it could bend even the elusive paths of dark matter particles, herding them into dense clouds around black holes. Simulations show these halos might distort spacetime subtly, creating gravitational fingerprints detectable by observatories like LIGO or future missions. The twist: some models propose primordial black holes, tiny, ancient black holes born in the universe's first seconds, could be dark matter, their collective gravity mimicking the effects we observe. The idea isn't as far-fetched as it sounds. If dark matter consists of primordial black holes weighing between an asteroid and a star, their event horizons would be too small to visibly accrete matter yet massive enough to bend light, a phenomenon called microlensing. Surveys like Ogle and Subaru's HSC have scoured the sky for these fleeting distortions, finding hints but no smoking gun. Yet the possibility lingers: could countless faint black holes, each with an event horizon no wider than a city, be hiding in plain sight? Then there's the wilder frontier, quantum interactions. Certain theories suggest dark matter particles might carry weak charges, allowing them to clump near event horizons and emit faint radiation as they annihilate. Others speculate that black holes could process dark matter, altering its properties over eons. If true, merging black holes might leave behind traces of this interaction in their gravitational waves, subtle ripples betraying dark matter's presence. The stakes couldn't be higher. If event horizons and dark matter are entwined, studying one could crack the code of the other, revealing not just where dark matter hides, but what it fundamentally is. Whether as cosmic traps, lenses, or even dark matter itself, black holes may be the key to illuminating the universe's darkest secret. And with telescopes peering deeper and detectors growing sharper, we might soon find the first hard evidence that these two mysteries are one and the same. Primordial black holes are the universe's ancient ghosts, tiny, mysterious remnants from the chaos of the Big Bang itself. Unlike the massive black holes born from collapsing stars, these hypothetical objects could be as small as an atom yet pack the mass of a mountain, their event horizons no wider than a speck of dust. Imagine a pinprick of darkness drifting through space, invisible yet so dense that its gravitational pull could shred anything that strayed too close. These little monsters wouldn't glow with accretion disks or warp entire star systems. They'd be stealthy, lurking in the void, detectable only by the ripples they leave in their wake. The theory behind them is as fascinating as it is unsettling. In the first milliseconds after the Big Bang, patches of the newborn universe might have been so intensely dense that they collapsed directly into black holes, no exploding star required. Some could have evaporated almost instantly, their Hawking radiation burning them away in a fleeting burst of energy. Others, with masses comparable to asteroids or even planets, could still be out there today, drifting undetected through galaxies. Their event horizons, though minuscule, would be just as lethal as those of their supermassive cousins. A primordial black hole passing through a star or planet wouldn't swallow it whole but would tunnel through like a bullet, leaving a trail of seismic shockwaves or strange radiation in its path. What makes these objects so intriguing and terrifying is their potential to rewrite cosmic history. Some scientists speculate they could explain dark matter, that elusive substance holding galaxies together. If countless primordial black holes pepper the universe, their combined gravity might account for the missing mass we've been searching for. Others suggest they could be the seeds of supermassive black holes, growing over billions of years by devouring gas, stars, and even each other. There's even a chilling possibility that one could be closer than we think, hiding in our solar system's outer reaches, its gravity subtly tugging at distant objects like an unseen puppeteer. Detecting them is a puzzle wrapped in a paradox. Their tiny size means they wouldn't emit the telltale X-rays or light bursts of larger black holes. Instead, astronomers hunt for their ghostly signatures in other ways, like microlensing events, where a primordial black hole's gravity bends light from a distant star, briefly magnifying it like a cosmic magnifying glass. Some experiments even listen for the echoes of their collisions, the faintest whispers of gravitational waves rippling through spacetime. Yet for all their mystery, primordial black holes push us to confront the universe's extremes. They remind us that black holes aren't just stellar corpses but could be cosmic fossils, relics of a time when the universe was hotter, denser, and far more volatile. And if they're real, they could be threading through the cosmos right now, unseen and unstoppable proof that sometimes the darkest things in the universe come in the smallest packages. When two black holes orbit each other in a cosmic dance of death, they don't just collide, they warp the very fabric of the universe. These titans spiral closer, their immense gravity stretching spacetime like a trampoline with bowling balls rolling toward the center. As their event horizons draw near, the distortions become so violent that they send ripples cascading outward at the speed of light gravitational waves, first predicted by Einstein a century ago but only detected in 2015. These waves aren't mere tremors, they're full-throated roars in the silence of space, carrying secrets about how black holes merge and what happens when their event horizons finally touch. Picture the final moments before merger. The black holes, each with an event horizon from which nothing escapes, circle faster and faster, reaching speeds close to light itself. Their gravitational pull is so intense that they don't just orbit, they churn spacetime into a chaotic whirlpool, dragging the entire region around them in a swirling frenzy. The event horizons stretch toward one another, no longer smooth spheres but distorted into teardrops by tidal forces. Then, in a fraction of a second, they meet. At that instant, the horizons merge into a single, wildly contorted shape, a peanut-like bulge of spacetime that rapidly smooths into a larger black hole. This event, known as the ring-down, sends gravitational waves rippling outward like the dying vibrations of a struck bell. The energy released is staggering. In that split-second collision, the merging black holes can convert several times the mass of our Sun directly into gravitational waves. To put that into perspective, the famous 2015 detection by LIGO, a chirp lasting less than half a second, represented more power than all the stars in the observable universe shining combined for that brief moment. And this wasn't some rare cataclysm. Scientists now estimate these mergers happen roughly once every 15 minutes somewhere in the cosmos, a constant drumbeat of spacetime shaking beneath everything we see. But the real magic lies in what these waves reveal. Each merger leaves a unique fingerprint in the gravitational signal, a pattern that tells us the black hole's masses, spins, and even how they were born. Some pairs might have started as binary stars that collapsed and spiraled inward over eons. Others could be rogue black holes flung together in the crowded core of a galaxy. The way their event horizons interact during the merger, whether they spin in alignment or clash at odd angles, paints a vivid picture of their history. These collisions also push Einstein's theories to their limits. General relativity predicts that merged black holes should quickly settle into a quiet, symmetrical state, a perfect sphere of darkness. But if tiny deviations are found in the ring-down, it could hint at new physics, like exotic matter or hidden dimensions warping spacetime in ways we don't yet understand. Some scientists even speculate that the event horizon surface might briefly fragment during the merger, creating fleeting wormholes or quantum bridges before sealing shut forever. What's astonishing is how far we've come in observing these invisible dramas. Just a few decades ago, black hole mergers were purely theoretical. Now, thanks to instruments like LIGO and Virgo, we've catalogued dozens of events, each one a snapshot of spacetime's most violent transformations. Future detectors like the space-based LISA mission will listen for the mergers of supermassive black holes collisions so immense their waves could take years to pass through our solar system. These ripples in spacetime aren't just cosmic curiosities. They're echoes from the edge of reality, teaching us how black holes grow, how galaxies evolve, and perhaps even how the universe itself is woven together. Every merger is a reminder that out there in the dark, gravity is rewriting the rules right before our eyes, and we're finally learning how to read them. What if every bit of information that falls into a black hole isn't lost, but instead gets stamped onto its event horizon like a cosmic fingerprint? This is the startling premise of the holographic universe theory, a concept that reimagines reality itself as a two-dimensional projection. The idea flips our intuition on its head. Instead of seeing the event horizon as a boundary where matter vanishes, it suggests this surface acts like a high-resolution hard drive, encoding every particle, every atom that crosses it in a swirling, microscopic script. The theory traces back to the work of physicist Gerard T. Hooft and later Leonard Susskind in the 1990s, wrestling with Stephen Hawking's black hole information paradox. If quantum mechanics insists information can't be destroyed, then black holes must preserve it somehow. But how? The holographic principle proposes an elegant, if mind-bending, solution. Just as a credit card's hologram holds three-dimensional information on a flat sticker, the event horizon could store the data of infalling objects in Planck-scale pixels, each no larger than a trillionth of a meter. Picture tossing a book into a black hole. In classical physics, its pages would be shredded and compressed beyond recognition at the singularity. But the holographic universe theory argues that the book's information, every word, every ink molecule gets imprinted onto the horizon's surface in a scrambled quantum code. The three-dimensional book is gone, but its essence lives on, etched into the black hole's two-dimensional skin. Over time, as Hawking radiation leaks energy, this encoded data might even trickle back into the universe like smoke signals from beyond the void. What's truly radical is how this idea scales up. Some theorists argue that if black holes can store information holographically, perhaps our entire universe does too. Imagine standing in a room with holographic wallpaper. Every object, every movement inside the room is actually encoded on the walls themselves. In this view, the three-dimensional world we experience could be a projection from a two-dimensional surface at the universe's edge. It's as if reality is a cosmic illusion, with the event horizon serving as a template for how information structures spacetime itself. The implications ripple across physics. If the holographic principle holds, it could bridge general relativity and quantum mechanics by redefining spacetime's fabric. Instead of infinitesimal points, space might be woven from interconnected bits of information, like a cosmic mesh where every node stores data. This aligns with string theory's notion that particles aren't dots but vibrating strings, their harmonies written into the universe's underlying code. Even gravity, which Einstein described as spacetime's curvature, might emerge from how this information interacts, like heat arising from atomic motion. Critics counter that the theory, while mathematically compelling, lacks direct evidence. How do you test whether the universe is a hologram? Surprisingly, experiments are underway. Fermilab's holometer, for example, hunts for spacetime pixelation by searching for quantum noise in laser beams, a potential signature of information's granular structure. Other researchers analyze cosmic microwave background radiation for anomalies that might betray a two-dimensional origin. Whether the holographic universe is literal or metaphorical, it forces us to reconsider what reality truly is. Are black holes monstrous erasers or the universe's most sophisticated archivists? The answer might rewrite not just astrophysics, but philosophy itself, blurring the line between the tangible and the encoded, between what we see and where it's really stored. Black holes might seem like cosmic oddities, dark anomalies lurking in the void, but they could play a starring role in the universe's final act. Whether the cosmos ends in a frozen whisper or a violent crunch, event horizons may hold the key. Picture the far future, trillions of years from now, when stars have burned out, galaxies have scattered, and the universe is a vast, dark graveyard of dead suns and wandering black holes. In this frigid era known as heat death, black holes would be among the last beacons of structure, their event horizons standing as silent monuments to gravity's enduring grip. But even they wouldn't last forever. Thanks to Hawking radiation, black holes slowly leak energy, evaporating over incomprehensible timescales. A stellar mass black hole might take 10 to the 67 years, a 1 followed by 67 zeros, to fade away. Supermassive black holes even longer, but as they shrink, their evaporation accelerates, culminating in a final, explosive burst of particles. In this scenario, the last flickers of light in the cosmos might come not from stars but from dying black holes, their event horizons winking out one by one until nothing remains but a sea of drifting photons, stretched and cooled to near absolute zero. The universe would reach maximum entropy, a state where no energy can be extracted, no work can be done, and time itself becomes meaningless. But heat death isn't the only possible finale. Some theories suggest the universe could collapse back in on itself, reversing the Big Bang in a cataclysmic Big Crunch. Here, black holes could act as gravitational anchors, pulling matter together until spacetime itself crumples. Imagine a future where galaxies merge, their central black holes spiraling into one another, creating ever larger event horizons that dominate entire regions of space. These behemoths would devour everything in their path, growing until the cosmos is a tangled web of singularities. Eventually, even those might coalesce into a single, universe-spanning black hole, its horizon swallowing all of reality before collapsing into an infinitely dense point, a mirror of the singularity that birthed the Big Bang. There's even a wilder possibility that black holes are the seeds of new universes. Some models in quantum gravity suggest that inside every singularity, spacetime might rebound, birthing a fresh cosmos with its own laws of physics. In this view, our universe could be the offspring of a black hole in some higher dimensional realm, with event horizons acting as cosmic wombs. If true, black holes wouldn't just be endpoints, they'd be portals, recycling destruction into creation in an endless cycle. The truth is, we don't know how the story ends, but black holes and their event horizons are more than just destroyers. They're sculptors of cosmic fate. Whether they herald eternal silence, a fiery rebirth, or something beyond our current imagination, they remind us that the universe's most dramatic chapters are written in gravity's invisible ink. And as we peer into the abyss, we're not just studying the end, we're glimpsing the deepest rhythms of existence itself. Einstein's general relativity describes the event horizon as a silent, unremarkable threshold, a place where spacetime bends so severely that nothing can escape, yet where a passing astronaut would notice nothing unusual. But quantum mechanics paints a far more violent picture. In 2012, physicists Ahmed Almary, Donald Marolf, and others dropped a bombshell. What if the event horizon isn't smooth at all? What if it's a searing wall of energy, a firewall of high-energy particles that would incinerate anything daring to cross? This radical idea didn't just tweak existing theories. It set them on fire, exposing a fundamental rift between gravity and quantum mechanics that physicists are still scrambling to reconcile. The firewall paradox arises from a seemingly innocent question. What happens to quantum entanglement near a black hole? Empty space isn't truly empty. It's a bubbling sea of virtual particles that constantly pop in and out of existence. Normally, these particle pairs annihilate each other instantly, but near an event horizon, one particle might fall in while the other escapes as Hawking radiation. Here's the catch: quantum mechanics insists these particles remain mysteriously linked, no matter how far apart they drift, a phenomenon called entanglement. But if the escaping particle carries away energy, the black hole loses mass, meaning the infalling particle must somehow sever its entanglement with its partner to avoid violating quantum rules. The proposed solution, a blistering firewall at the horizon where quantum corrections to gravity ignite a boundary of unimaginable heat, shredding anything attempting to pass. This idea horrified many physicists, including Stephen Hawking himself. Einstein's equations treat the event horizon as a mathematically smooth surface, no fireworks, no drama. An astronaut crossing it wouldn't feel a thing until tidal forces ripped them apart much later. Firewalls demolish that elegance, suggesting a horizon so lethal it contradicts relativity's core principles. Critics argue that if firewalls exist, they'd make black holes glaringly visible, radiating energy in ways we've never observed. Others counter that firewalls might only form under specific conditions, like when a black hole is old and saturated with entangled particles, or that they could be transient, flaring up only during interactions with infalling matter. The debate cuts to the heart of physics' greatest challenge, uniting general relativity with quantum mechanics. Firewalls force us to confront whether spacetime is fundamentally smooth or granular, whether information is truly indestructible, and whether black holes are cosmic killers or quantum enigmas in disguise. Some theorists propose wild alternatives like fuzzballs, a string theory concept where black holes are tangled knots of energy without singularities, or soft hair, subtle quantum imprints on the horizon that preserve information without fiery extremes. For now, the firewall remains a specter haunting theoretical physics, a paradox that refuses easy resolution. It's a reminder that at the edge of a black hole, our best theories clash violently, and the answers might require rewriting the rules of reality itself. Whether firewalls exist or not, their mere possibility has already scorched old assumptions, proving that even the darkest corners of the universe can ignite the brightest debates. Black holes have dominated astrophysics for decades as the ultimate cosmic vacuum cleaners, but what if they're not the only explanation for the dark, dense objects lurking in space? A handful of bold theories propose alternative monsters that defy the traditional black hole model, each with its own quirks and consequences. Take gravastars, for instance. These hypothetical objects ditch the crushing singularity and event horizon entirely, replacing them with something far stranger, a bubble of exotic dark energy encased in a shell of ultra-dense matter. Picture a rubber ball filled with vacuum energy, the same mysterious force accelerating the universe's expansion but compressed to unimaginable densities. The outer layer mimics a black hole's gravity, bending light and trapping matter in tight orbits, while the interior remains paradoxically hollow. No singularity, no point of infinite density, just a bizarre cosmic matryoshka doll where spacetime takes on properties unlike anything we've observed. Then there's the dark energy star, another radical reimagining of cosmic collapse. Instead of forming a singularity, a dying star's core might reach a critical density where dark energy, the anti-gravity force stretching the universe apart, suddenly dominates. The result, an object that looks like a black hole from the outside, with intense gravity and light-bending effects, but lacks an event horizon. Matter falling in wouldn't vanish forever. It'd hit a swirling maelstrom of dark energy at the core, potentially being ejected or transformed in ways black holes can't explain. Some versions of this theory even suggest dark energy stars could power cosmic jets far more energetic than those from black holes, offering an alternative explanation for phenomena like quasars. But perhaps the most mind-bending challenger is the Planck star. This idea, rooted in loop quantum gravity, proposes that collapsing stars don't form infinite singularities but rebound at the smallest possible scale, the Planck length. Imagine a star compressed to a trillionth of a meter, where quantum effects overpower gravity, causing a bounce. From the outside, it'd still resemble a black hole, complete with an apparent horizon, but the interior would host a fleeting, ultra-dense remnant of the original star, slowly evaporating over eons. The kicker, this model suggests black holes might eventually explode, releasing their trapped matter in a cosmic encore billions of years after formation. Why consider these alternatives? For starters, they sidestep some of black holes' thorniest problems, like the information paradox and the singularity's mathematical absurdities. Gravastars and dark energy stars preserve information naturally, since nothing crosses an unrecoverable horizon. Planck stars eliminate singularities entirely, keeping physics finite and tidy. And then there's observational ambiguity. Despite the stunning image of M87's shadow, we still can't peer past an event horizon to confirm what lies beneath. Alternatives predict subtle differences like the way light echoes around their surfaces or how they vibrate when colliding, that future telescopes might detect. That said, these theories aren't without flaws. Gravastars require exotic matter with negative pressure, a substance we've never observed. Dark energy stars lean heavily on the still mysterious nature of dark energy itself. And Planck stars hinge on untested quantum gravity models, yet their very existence as plausible challengers highlights how much we still don't understand about gravity's extremes. They push us to ask, are black holes truly the universe's only answer to gravitational collapse, or are we just seeing one side of a stranger, richer reality? The beauty of these ideas isn't just in their novelty, it's in how they reframe the conversation. If gravastars or Planck stars exist, they'd force us to rewrite textbooks on stellar evolution, dark energy, and quantum physics all at once. Even if they're wrong, the questions they raise refine our search for the truth. After all, science thrives not on dogmas but on daring to imagine and test what might lie beyond the event horizon of current knowledge. Black holes don't just bend space-time, they warp our understanding of existence itself. The moment we confront the idea of an event horizon, we're forced to grapple with questions far beyond physics. What does it mean for humanity if there are places in the universe where reality, as we know it, simply ends? These cosmic abysses challenge our deepest assumptions about time, identity, and the very nature of meaning. Imagine standing at the edge of a black hole, staring into a void where the laws that govern our lives cease to apply. It's a confrontation with the sublime, an encounter so vast and indifferent that it reshapes how we see ourselves in the grand scheme of things. Consider time dilation near the event horizon. A traveler falling in might experience mere minutes while centuries pass for those left behind. This isn't just a quirk of relativity, it's a philosophical grenade. If time can stretch and fracture so dramatically, what does that say about the permanence of our choices, our relationships, even our legacies? The universe, it seems, has no universal clock. Your life, your history, could be a fleeting footnote in someone else's timeline, erased by the gravitational whims of a distant monster. It's a humbling reminder that our narratives of progress and permanence are fragile constructions, easily unraveled by forces beyond our comprehension. Then there's the information paradox, which strikes at the heart of what we consider knowable. If a black hole swallows a star, a planet, or even a hypothetical civilization, is that information truly lost forever? Quantum mechanics insists it can't be, but relativity offers no escape route. This isn't just a technical dispute, it's a battle over whether the universe is fundamentally predictable or inherently chaotic. Are we living in a cosmos where every event leaves a trace, or one where entire chapters can vanish without a whisper? The answer could redefine everything from thermodynamics to the nature of memory itself. Ethically, black holes force us to confront the limits of exploration. Unlike distant stars or exoplanets, these objects aren't just difficult to reach, they're inherently hostile to life and inquiry. Sending a probe past the event horizon isn't just risky, it's futile. No data could ever return, no discovery could be shared. It's the ultimate one-way mission, a sacrifice with no possibility of reward. What does that say about our drive to uncover the universe's secrets? Are there frontiers we're not meant to cross, not because of technological limitations, but because the cosmos itself refuses to cooperate? On a grander scale, black holes expose the tension between beauty and terror in the natural world. Their elegance, the way they sculpt galaxies, power quasars, and even potentially seed new universes, exists alongside their brutality. A single black hole could erase a star system without a trace, its gravitational waves the only epitaph. This duality mirrors humanity's own relationship with the cosmos, awe and fear, curiosity and humility, all tangled together. We're drawn to these objects not despite their danger, but because of it. They're mirrors held up to our deepest existential fears of oblivion, of insignificance, of forces beyond our control. Perhaps the most unsettling question black holes pose is whether the universe is fundamentally comprehensible. For centuries, science has operated on the belief that nature, no matter how complex, follows rules we can uncover. But what if some phenomena, like the singularity at a black hole's core, are forever hidden behind mathematical firewalls? Does the cosmos contain truths that are, by their very nature, unknowable? Or is this just a temporary gap, a challenge for future generations to solve? The event horizon isn't just a boundary in space, it's a threshold for human thought, daring us to imagine a reality where not everything can be explained, only accepted. In the end, black holes do more than consume matter. They devour our assumptions, forcing us to rebuild our understanding from the ground up. They remind us that the universe isn't just stranger than we imagine, it's stranger than we can imagine. And in that strangeness lies an invitation to keep questioning, keep exploring, even when the answers lie forever out of reach. You've probably heard some wild claims about black holes, that they're cosmic vacuum cleaners sucking up everything in sight, or that crossing the event horizon means instant spaghettification. But let's clear up a few myths. First, black holes aren't roaming the galaxy gobbling up planets. Even if our sun magically collapsed into a black hole today, Earth would keep orbiting just fine. Gravity doesn't suddenly get stronger because something becomes a black hole. The danger isn't in their reach but in their edge, the event horizon, where gravity's grip becomes inescapable. Another common mix-up, thinking the event horizon is a solid surface. It's not some glowing ring you'd bump into like a galactic force field. It's a mathematical boundary, invisible and intangible. You wouldn't even realize you'd crossed it, at least not until tidal forces started pulling you apart, and even that depends on the black hole's size. Smaller black holes shred you before you reach the horizon. Supermassive ones might let you drift deeper before the stretching begins, and let's tackle the big one. Nothing escapes a black hole. Strictly speaking, that's almost true, but Hawking radiation means they're not entirely black. They emit tiny amounts of energy over unimaginable timescales, slowly evaporating. It's not much, but it's proof that even the universe's ultimate prisons have a leak. Now, what about you? What questions or myths have you heard? Drop them in the comments. Maybe you've wondered if black holes can die. They can, over eons. Or if wormholes could really hide inside them. The math allows it, but reality's trickier. This is your chance to dig deeper, and who knows, your question might just spark the next segment. The universe is full of mysteries, but the best ones start with curiosity. So tell us, what's your take on the great black hole debate? From the moment we first imagined black holes to the day we captured their shadows, event horizons have defied our intuition and reshaped our understanding of reality. These invisible boundaries represent more than just points of no return. They're cosmic laboratories where the universe tests its own rules, pushing physics to extremes we're still struggling to comprehend. Think about it, a place where time stretches like taffy, where light surrenders to gravity's grip, and where matter vanishes from our observable universe while still shaping the fate of galaxies. The very existence of event horizons forces us to ask questions that straddle the line between science and philosophy. What happens to the information they consume? Do they truly erase it, or is reality more resilient than we thought? The significance of these mysteries stretches far beyond academic curiosity. Every breakthrough in understanding event horizons, from Hawking's radiation to the holographic principle, ripples across physics, touching everything from quantum computing to cosmology. These strange surfaces might even hold clues to unifying general relativity and quantum mechanics, two pillars of modern science that refuse to play nicely anywhere else. And let's not forget their role as cosmic architects. Supermassive black holes, anchored by their event horizons, sculpt entire galaxies, influencing where stars are born and how solar systems form. Their gravitational might shapes the universe on scales we're only beginning to map. Yet for all we've learned, event horizons remain tantalizingly out of reach. We can model them with equations, simulate them with supercomputers, and even photograph their shadows, but the true nature of what lies beyond remains one of science's greatest unknowns. That's the beautiful paradox of studying these cosmic frontiers. The more we uncover, the more we realize how much we've yet to discover. Perhaps that's why black holes captivate us so deeply. They're not just objects in space, they're mirrors reflecting the limits of human knowledge, reminding us that wonder and curiosity are the engines of progress. So where does that leave us? At the edge, quite literally, of a vast unknown. Whether you're an astrophysics enthusiast or just someone who gazes up at the night sky with questions, remember this: every revolutionary idea starts with a simple "what if?" The event horizon teaches us that the universe is far stranger and far more wonderful than we could have imagined. And as telescopes grow sharper, as simulations become more sophisticated, who knows what revelations await? The next chapter in this story might be written by someone watching this right now, someone who dares to question, to explore, to push beyond the boundaries of the known. After all, that's how we got here in the first place. The universe's greatest mysteries aren't meant to intimidate us, they're invitations to look deeper. So stay curious, keep wondering, and never stop asking what lies beyond the next horizon. The adventure's just beginning.